Well, back in 1981, the November QST issue had an article on a progressive receiver. And I thought, oh, I'd like to build that. Anyway, it's been a little while since 1981. And, but anyway, I always wanted to do it, and I thought, well, I'm going to give it a go. And so I've been working on this in fits and starts for probably the past 5 or 6 years, but I finally got serious about it a little while ago. And anyway, so let me explain to you what a progressive receiver is. It starts off with something pretty simple, 80 meter direct conversion receiver. And it basically has just a few components. It has a prescaler, which is like a peaker, an RF peaker. It has a mixer and a VFO that you can build for various frequency ranges. The one I built is for 3.5 to 4 megahertz, which of course that's the 80 meter band. And then it's got a product detector, a really poor audio amplifier, and you can decide to build some active audio filters, which I did. And so,
what's with the variable capacitor between your preselector and VFO?
This is a 365 picofarad variable capacitor, which is part of the preselector, and it's actually this right here. Yeah. So right. And I'm going to talk a little more about this because that was one of the first little hiccups that I ran into. But anyway, the radio to date, as you see it, is this right here. It's a working 80 meter direct conversion receiver with two active audio filters, one for CW and one for sideband. And actually works pretty good. I mean, you know, it's what it is. Now, just to give you an idea of how simple this is, see if I can blow this up just a little bit. You've got your RF coming in here and your VFO coming in here, and this is a Mini Circuits SBL1, which maybe you've used in the past, and it's a diode ring mixer. And basically, what you get out on the other side of this RF choke is audio, which very weak, of course, has to be amplified. And so you come in through a couple of stages. You've got a mute stage here, and your volume control right here. And if you want to use the active audio filters, you would actually insert them right before the volume control. And then you've got 2 stages of audio amplifier and the output. And the output is good to drive some cheap headphones, but it won't drive a speaker. So I've got to do something about that. But anyway, that's for later on. So this is just kind of showing you how simple the actual product detector part of it is.
So is there a BFO in there then?
No BFO. No, it's just this is just you're going to take the VFO and beat that up against the incoming RF, and the difference is your audio.
Okay.
Now, before I go too far, I'm going to start pass this around. You're going to see the main tuning capacitor and the VFO board right behind it, and then the pre-selector. That's this board up in the far corner here, and the capacitor is attached to it, the 365 picofarad capacitor. And I'm going to talk a little bit more about this in a minute. And then that's followed by a sideband active filter, a CW active filter, and this is the product detector and audio amplifier, the large board here. Now, with that successfully built, then you want to turn it into a super hat. And to do that, you have to add some stages. So there are two types of input filters that are designated for the radio. One is a passive input filter, which is basically a tuned circuit. That's for 40 meters and 30 meters. And then for everything above that, then you've got an active input filter, and that's essentially the same thing as the passive, except it adds a stage of amplification. Down here you have your converter oscillators, and I've only showed two, one for 40 and one for 10, but you have one for every one that you want, every band that you want. And that's where I ran into my very first problem. I discovered I couldn't get the crystals I needed. So I thought about that, and then I thought, well, I'm going to have to go kind of high-tech, and I decided I would use one of these SI 5153 modules, and then I could, get whatever frequency I needed. But that did throw a little fly in the ointment. Anyway, you've got your first mixer here, and then that gives you an 80-meter IF output. And that goes to your pre-selector, and then your second mixer, and your second mixer gives you a 9 megahertz IF output, which in turn is fed to crystal, 9 megahertz crystal filter, which was another little fly in the ointment for me that I had to figure out. And then
Is there a reason you selected 9 megahertz as your IF?
that's the way the author initially.
Oh, okay.
It's a very common frequency.
Yeah.
So at a certain time in history, they were really common, the filter.
And you can get the 9 megahertz crystals, which is good. Well, anyway, you come into a 9 megahertz crystal filter, and there I'm going to show you the different ones that I've tried and so forth. And then that goes to your IF amplifier, and then your product detector, which requires a BFO for either upper or lower sideband. And the BFO board that I built it's the same circuit as used for the other the converter oscillators, if you could get the crystals. But I'll describe a problem I ran into with this right here in a minute. Anyway,
What's your bandwidth then through that crystal filter?
it's pretty narrow, and I've got a shot for you to look at here, and pretty quick. Anyway, the output goes to your audio frequency amp, and then your active filter for CW or sideband, if you choose to do that, and then your audio amplifier. And that's your super het part of it. So I've got all the boards built for the super het side of it. Here's the IF board. I'll pass that around. But the requires about 6 other little subboards, and I did all of the boards in KiCad, and I had them built by All PCB, and they really make a nice board. You can see that that's a nice board there that they send you.
Steve, what are you using for your AF amp that feeds the speaker?
Right now, just the small audio stage that is on the board. That's but at some point in time, I've got to do something different, because what I'd like is about 3-4 watts of audio power, on account of I don't hear well, so. But that's the super het side of it, which I'm working on now. Now, I don't know about you guys, but I've built some kits and whatnot that had active audio filters, and I always questioned how well the audio filter response was. So I thought, well, okay, I've got 2 audio boards, one for CW, one for sideband. Let me just plot it out and see what the actual response is. And so I did that. Here's the sideband one, and you can see that it peaks at 1,650 hertz, and then it falls off pretty quick after that. And on either side of the 3 dB mark, or the 6 dB mark, there's nothing there. It's a pretty tight filter. And then here's the CW response, and the CW response peaked at 784 hertz and falls off on either side pretty quick. And when you listen to it and you switch between it, and by the way, that one wired up function switch, that is switching between the filters, you can switch it off at sideband or CW. You really hear the difference with it. It's quite pronounced. Now, let me get back to this preselector here for a second. The preselector, and you can see it's all wired up in there, but I'm going to pass around the board. back in 1981, they called for mica capacitors, silver mica capacitors. And well, I couldn't get a silver mica capacitor. I mean, you can order them up, but they're very expensive anymore. And so I thought, well, let me see about ceramic. Well, they wanted these oddball values. So I thought, how am I going to do that? So I thought, well, let me put a couple together. So I'm going to pass this board around. You're going to see that I've got capacitors in parallel, which allow me to put, a couple of caps in to get the value I needed.
Adam,
Yeah. And I was able to get pretty much right on the money with the value I needed. And when I got all done with that, I thought, well, how well does this work? So I put it on the spectrum analyzer, and this thing is sharp. This is the peak right here, and the start frequency is 2 megahertz, and the stop frequency is 5 megahertz, and it falls off pretty rapidly. And if you're actually using the receiver and you tune that cap, you'll see this move back and forth, and it's really sharp. It's a very sharp preselector. So I can see why the author wanted to include that.
what was the other side? You have an inductor then that was parallel with the capacitors or in series with?
Well, it's a multi-section filter. It's actually got 6 coils and as many capacitors plus the tuning cap.
And do the coils demand the precision that the capacitors did?
Well, if you take care in winding them, you get pretty close. Yeah. I mean, I was very pleasantly surprised when I.
Peaked out where it was supposed to peak out?
Yeah, when it looked the way it was supposed to look on the spectrum analyzer, and then in the radio, actually tuning in stations, it worked as advertised. So yeah. Now, one of the you probably noticed that I've got a digital frequency readout there, and yeah, I got that for like $12 from AliExpress, and it's surprisingly accurate. I mean, it's when I compare it against, I've got a frequency counter on the bench that's GPS disciplined. It's within, a couple of hundred hertz. So, I mean, that's not bad for $12. Anyway, when I first turned I got it all wired up, and I turned the whole thing on, all I got was this horrible howl out of the audio, and I said, what did I do wrong? And so I'm poking around and looking and trying to figure out what was going on. Well, finally, it dawned on me it was noise coming from the frequency counter. And so I don't know if you noticed, but stuck onto the front panel is a little board. And so what I had to do was build a little filter to keep the noise contained. And that took care of the howl and whatnot. But actually the noise wasn't that large in amplitude, but it was appearing on the power line, the 12-volt line. So anyway, a little pie filter took care of that. And yeah, I just used some stuff out of my junk box. Now, the crystal filters, when you read the article, and it's a good article if this is sort of thing that you're interested in, they say, well, you can buy one of these, commercial ones. Well, yeah, I guess you could for a few $100s. So I thought, well, what's the way around that? Well, I started Googling, and Wes Hayward wrote 3 really good articles on crystal filters and making them and that sort of thing. And Wes Hayward wrote another article which I found really useful. So I thought I'd include those in case anybody was interested. But the concept is that you have to, build a 9 megahertz crystal filter. So one of the first things you have to do is match filters. And so a while back I built a crystal checker, which I ended up mounting on a little piece of sheet metal. But this is all it is, and if you're wondering, this thing here is this is a 8-pin IC socket that you can stick the crystal into, and the switch is just switches in or out this little capacitor. Anyway, you can now easily check crystals. So the first thing I did was I thought, well, let me order up some crystals from DigiKey. So I ordered up 10 crystals from them, and they're a little on the spendy side. I figured I'll order 10 and I'll see, how close are they. And so what I did was I took a piece of styrofoam and divided it into grids. There's 100 squares here, and that represents the last 1 kilohertz, right? So the crystal should fall somewhere in that grid when you test it. And you can see that the crystals I got from DigiKey were all kind of on the low end. But I did find some, I took 3 out of that batch and actually built a nice filter. AliExpress had 50 crystals for like $3 and change, and I thought, wow, So I ordered those up, and out of the 50, there were 3 that were deader than a doornail, but the rest of them, you can see how they distributed around there. And anyway, none of them are.
What's the range represented there?
8.9998, and then the last 999.
8.9 to 9.9, or
Yeah.
9 to 9.9.
Yeah, yeah, exactly. So, but you can see this distribution was, much wider. Anyhow,
But couldn't you just take several that were nearly alike and then adjust your circuit intentions?
that is possible, but difficult. So what you want to do is you want to get them, so if you want to build a 300 or 500 hertz CW filter, ideally you'd want the crystals to be within 50 hertz of one another.
Now, what I was getting at is you got 50 of them, and they're spread out, but you probably have several at different frequencies that are very similar.
Correct. And those are the ones you use.
Yeah.
Right. So here's a 300 hertz Butterworth CW filter, which is the simplest one I built. And I'll pass that around. And you can see here the center frequency is 9 megahertz, and it's narrow. It's a narrow filter. Whoops.
Steve, these pictures you're showing us, it looks like this is all Riggle instrumentation. Is that a scope and an analyzer, or is that one?
No, this spectrum analyzer, and it's got a internal generator, so yeah, tracking generator. And then the other Riggle I've got is MSO type. Two separate instruments, right. Now, whilst I don't know, surfing on AliExpress, I found this sideband 9 megahertz filter for like, I don't know, $12 or $13, and I thought, well, you know, what the hey, so I ordered it, and this is the response. So it looks pretty good. Time will tell when I put it in the circuit. And then I had 4 crystals that were fairly close to each other, and I thought, well, I'll build this 2000 hertz Chebyshev filter, and this one required impedance matching transformer at the input and output, and this is the response here, and this is more centered over 9 megahertz than the AliExpress one. And this is showing it with a little expanded view of it.
You have that little jog on
Yeah.
one side or the other.
Yeah.
What the deal is with that?
I don't really know, but that seems to be typical of the
Yeah.
crystal filters.
Yeah, well, and even other filters, I mean,
Yeah.
non-crystal filters.
Yeah.
I was hoping you could give me the answer to that.
But the bandwidth, I don't know if you can see it, the bandwidth here for this is 3 kilohertz. So it's, you know, anyway, there's a company, maybe you guys have heard of it, called Minikits in Australia. And they sell a 9 megahertz filter which can be configured for AM, sideband, or CW. And it's a kit. And I actually ordered this up several years ago, but I never built it. But I built it here the other day, and it's got some parts on it that are so small, I have no, yeah, I don't know. But anyway, when I checked the crystals, these guys were really matched. I mean, they were matched within like 30 hertz of each other. And so, yeah, I'm hoping that works out good.
This is a 3 kilohertz filter.
This one is give you 500 hertz for CW and I think 2.3 for sideband and 6 for AM. It's got some logic switching on it that you can do. Now, all of this required just a little bit of thinking about capacitors, and I've forgotten most of what I knew about capacitors, but when I started with the pre-selector and it asked for mica capacitors, I thought, geez, what was so special about micas? Well, number one, their tolerance is very good, and number two, they don't drift with heat or temperature change as much as others. But they are expensive, they're kind of hard to get anymore. But I did learn that you can get them in surface mount. And then ceramic capacitors, well, that's those are the values that I was interested in, were, also available in ceramic. So I thought, well, okay, like I got XR7 capacitors, so what, X7Rs, right? What's the deal with that? So then I did a little Googling, and a lot of your capacitors are what they call class 2 and class 3, where the first character is the lowest temperature, the second character indicates the maximum temperature, and then the third character tells you how much it's going to fluctuate with temperature change, right? So you'll see in a minute there's some capacitors that are not any good for our purposes. Class 1 ceramic capacitors are designated as COG, which doesn't mean anything. I thought COG stood for something, but it doesn't. Whereas NPO stands for negative, positive, zero. If you go to the DigiKey site and you're selecting capacitors, they have a selection called COG/NPO. And
Maybe the COG is class 1 grade, something like that.
I have no, I Googled it, and it said that it did not stand for any acronym. Now, whether that's correct or not, who knows?
Well, if it's on the internet, it has to be true.
Right.
Yes.
It's all at the same time.
Anyway, the bottom line is the capacitance is not affected much by temperature, voltage, or aging. So that's a good capacitor if you're building an oscillator or something that's frequency dependent. Now, the smallest stock you used to be able to get in surface mount was 1206, which I can't do anything with anything smaller. It's too small. But you can get them smaller than that now, I found out. Now,
6, is that something you can handle with your fingers?
with a tweezer. With a tweezer, yeah, I can't. Yeah, they're so the caps on the crystal filters that I passed around, those are 1206 size. Anyway, so this is showing you temperature, and this is change. This line here is your ambient temperature. So you can see some caps like Y5Vs and Z5Us. If you're building anything that's not going to be all the time at room temperature, it's probably not a good cap to use. The X7Rs, I've got a whole potload of these that I use for bypass capacitors, and they're probably okay for that. And then down here, these lines are showing your COG NPO, and these are very stable. So
And what temperature range is represented on that bottom scale?
I don't know. I don't know.
What are the numbers?
Well, if we did like an X7R, that would be like from almost boiling down to really cold. And the X7Rs are fairly stable.
I was more concerned with the numbers on the very bottom line.
Oh, these aren't really numbers down here. They're just dash lines indicating cog response. So showing it doesn't change much. So anyway, which gets, you think you've got something simple to work with, and one of the, even though I couldn't get the crystals for the, converters for the other bands, well, I had lots of 9 megahertz crystals for the BFO, so I thought, well, okay, I'll make a couple of these boards, and I'll have my upper and lower sideband BFO. So this is the circuit for it, and I don't know if you can tell, but it's a weird circuit. I don't know why they built this, but this is a crystal-controlled Hartley oscillator. And I've got no experience with crystal-controlled Hartley oscillators, but I was able to kind of figure out how it worked. And anyhow, I built the first one, and voila, beautiful, it worked, no problem. So I thought, okay, I'm going to build the next one. I built the next one, wouldn't oscillate. What's going on here? Wouldn't oscillate. I'm turning the trimmers. I'm checking to see, did I get the resistors in wrong? Did I put a capacitor in wrong? Are my trimmers bad? Because it's got 2 trimmers. It's got a trimmer here, and it's got one right here that allows you to push the crystal frequency a little bit.
So your primary is tapped and that's resonant?
Well, it's tapped. Yeah, it's the primary is tapped 7 turns up from the bottom. There's 35 turns total on it, and then the secondary's got 6 turns. So the next thing I thought was I screwed up winding the coil, So I took the coil out and I redid it, and nothing. And about that time, my wife called me for dinner, and then I thought, you know what? I'm going to change the emitter resistance. So I thought, I bet if I lowered the emitter, because it was, the transistor was forward biased, but it wasn't oscillating. But I thought if I lowered the emitter resistance a little bit, I might force it to oscillate. Well, it's got a 270 ohm resistor in the emitter, and I put a 100 ohm resistor in there, and bang, it oscillates. But it's oscillating at 5 megahertz. So I'm thinking, oh, all right, so I've got a timing problem, right?
What's the crystal?
9 megahertz.
9, and you're good.
Yeah, and I'm getting 5 megahertz.
Okay.
So I'm thinking, all right. So anyway, so I'm thinking, what's the main thing that's going to cause me grief? And it's these 2 caps. This guy here is a 56 picofarad fixed, and this guy is supposed to be 60 picofarad max for trimming. So I pulled the trimmer out, because, they're in parallel there. It's oscillating a little closer to, in other words, it came a little closer to 9 megahertz. All right, so I pulled a 56 picofarad out, and I thought, well, let me put in a 43 picofarad. I put in a 43 picofarad, and I got even closer. And then I thought, well, then the trimmer needs to be reduced, so I put in a small trimmer, about 15 picofarads, and bingo, we're right on, right where we needed to be. And so here's the crystal oscillator for the first one I built that worked out of the gate. Here's showing the spectrum and the harmonics. Here's the second one I built, that I had to mess with. And that's this one here, and you can see I've got resistor and a capacitor kind of sitting a little further above the board.
Your sine wave is prettier too.
Yeah, and this can be adjusted with the trimmer. And I should have done that before I took the picture, but I didn't. But anyway, yeah, if you adjust the trimmer, you can put all kinds of distortion into the sine wave.
Any clue why the second oscillator didn't? Any clue why the second oscillator did not operate the same? Or?
No, I don't. Honestly, I don't know. The boards are identical, right? The boards are identical, but it's not the first time I've run into this. I'll give you an example. When I built the VFO for this, it did oscillate out of the gate, no problem. But I couldn't get the range I wanted. 3.5 to 4. It was high, and so I had to monkey with the capacitors on that to get it into the 3.5 to 4 megahertz range that I wanted. And then I put it on, mounted it into the cab on a piece of sheet metal, and that changed it again, but fortunately within the range of the trimmers. So now I will say, you probably might ask, well, why didn't he put it in a aluminum box, which I probably should have. But you know what? That thing just sits there and hardly drifts at all. It's very stable. It's a very stable circuit. So anyway.
Well, you have the crystal on it.
I was going to make a snide comment. Did you say you were working with FM?
Well, what I am working with right now, which has really got me pretty well buffaloed, is one of these silicon 5351, and I'll pass this around. And this thing here, gives you everything from about 10 kilohertz up through, I don't know how many megahertz, 100 megahertz. And you can control it various ways. So first off was an Arduino Nano, because, there's some examples out there on the web that you could. Well, my preferred thing that I really want to do the code for, however, is in MicroPython, using maybe the little tiny Raspberry Pi, or maybe an ESP32. I don't know, but it's not. It's not as easy to me as I thought it was going to be. Plus, you really need to interface a display with it. Anyhow, that's my project right now. And once I get that all figured out, I think I'm going to rip the VFO out of here and use one of these as a VFO and a nice little LCD display. But anyway, that's what's been keeping me out of the bar.